Hello together. A lot of you guys wished for a very detailed CFD-DEM video. I really tried to put everything in one video, but as more and more work went into this video, it seems that this video is getting a bit too long, so I will divide it into parts. So this will be a small video series about the simulation of a fluidized bed. In fact, I will use the CFD-DEM simulation of a fluidized bed I already uploaded to Engineerdo.com, but I will adapt this to a new geometry, to new boundary conditions, and also to different bike material. It will be a bit like a real-life application where you don't start from a blank page, but always start with something you have and then adapt it to something new. The process of copy and adapt is usually the fastest way to go. I will use only open source software here, and for the CAD modeling I will be using Blender, because from the comments it seems that not everybody has access to a commercial 3D CAD program, and Blender should be capable enough to do this work what we are doing today. The CFD part will be in openFoam 5.x, the DEM part in Liggghts 3.8.0, and we also use the coupling. Installation videos on all of these programs you can find also on this channel. In the first part of this video series I will give a short introduction into the coupling folder structure, because openFoam itself can be a bit confusing if you are new to it, and the coupling files coming from the DEM and the coupling itself will not make it clearer. After this I will start with the downloaded file from Engineerdo.com, and we will start with the CAD modeling in Blender, and then we will switch over to the DEM part. The following parts 2 and 3 will then focus on the DEM, so explaining the DEM code, what needs to be adapted, and also the CFD part. And in the last part we will bring everything together, run a simulation and do the post-processing. If you want to get a personal training, you can visit our website. I will link it down in the video description, and there you can book a personal training where we explain everything to the detail, and that will get you a very good start into the CFD and DEM simulations. Okay, let's get started. Since this tutorial is more detailed and will show how you can set up a simulation based on a model which is similar but different, I will use the fluidized bed simulation that you can download from our website in the link below, and I will modify it to the structure which is shown under this logo here. The bottom of the structure will be filled with particles, and after the particles are settled, I will push air through the column of particles. This could be a reaction process where particles are steamed through by a gas stream. Before we get into the simulation itself here, I want to say a few words about the general structure of the simulation. openFoam really lives from its folder structure. All boundary conditions, the mesh, and all settings are stored in separated files, which then are grouped into folders. With the DEM simulation, another folder parallel to the CFD folder occurs. When we have a look to the fluidized bed folder, we can see that the two folders of the DEM and the CFD part are separated. Along this we also see a STL folder which includes the geometry files and can be considered as a backup if I accidentally delete the STL data files, which will be needed in both the CFD and the DEM simulation. The runme.sh and the par CFD-DEM run.sh are files to start the coupled simulation. To model a specific problem, it's useful to start with a working simulation and start making changes stepwise. The CFD folder on the left hand side contains 3 folders: System, Constant and Zero. In the System folder, the settings of the simulation are stored. For the coupled simulation, the control dict is from interest because it contains the time step. The Constant folder contains the mesh, the coupling properties and the gravitation. The Zero folder contains all boundary conditions. On the right hand side, the DEM folder holds the lights input script, the mesh exclude files, if they are needed, the STL folder for geometries, and the post folder for the result files. Now I will start with an overview on the example simulation. The very first step is to go to Engineerdo.com and download the example fluidized bed simulation, to start from something that actually works. In the section of a fluid simulation you can find the fluidized bed simulation article. If you want to get a bit of an insight of the simulation, I linked the explanation video in the beginning of the article. At the end you will find the download link. After the download you should extract the files to a useful directory. The next step should be to check if the simulation runs on your system. This could avoid to look for errors later. I open a terminal window by clicking with the right mouse button to the folder and choose Open in Terminal. To execute the simulation, I try to start it calling the runme.sh file by writing /.runme.sh. My system says that it does not have permission to execute this file. This comes from the lost permissions. To set them again, I change the permissions with chmod 777 runme.sh, which makes an executable file from a text file. The same must be done for the par CFD-DEM run.sh file. After this, I can call the runme.sh file again and it will be executed. The simulation starts with the decomposition process, which needs to be done for a simulation using the multi-core functionality. This simulation is set up for 12 cores. If you want to use less or more, you have to make changes in the par CFD-DEM run.sh file and the decompose par dict in the CFD systems folder. If you have more than 12 cores available in your system, you can proceed with 12 cores, which is totally fine. Now, after I run the simulation, I know that if I'm doing everything right, my new simulation should also run very well. To get rid of the simulation data that I produced so far, I enter the CFD folder and find the processor folders. They contain the results generated so far from the CFD side. I will delete them so that we can start with the blank folder here. The processor folders are created automatically and do not contain critical data. The rest of the folder can stay for now. In the main directory you also can find a log file. This can be deleted as well. The STL folder works as a storage for me for my generated or designed CAD files. These can be replaced by the new structure. Before I get rid of them, I want to show you what's in these files. Therefore, I open a new terminal window by clicking right and I open ParaView. What you can see here is a cylinder, closed on both ends with a lid. I can use a little eye symbol in ParaView to make the structures invisible. You can see now that the cylinder is closed by an outlet and an inlet. These structures, the inlet, the outlet and the cylinder, are used in openFoam for the boundary conditions and the automatic meshing with snappy hex mesh. They are also used in the DEM simulation and they will function as the walls there. One very important function of ParaView is that it can show the dimensions of the different meshes of my structure. This is important for fast modeling in the CFD as well as in the DEM. To see the dimensions, I select one part which is from interest. Here it is the cylinder, because I know that this is the largest object in every dimension of the coordinate system. If I go to the information tab, it shows me the numbers of cells and points. A lower number could be better for a faster meshing or DEM simulation. And it shows also the bounds in the lower figure. It is labeled for every coordinate axis individually. I can see now where my part begins, where it ends and how big it is. This function is also very important to check if you're using the right coordinate system, like meter, millimeter or inch or foot. The first step in all new simulation models is the import of a CAD structure that you or your fellows designed. The import of a CAD structure can sometimes be a bit nerve-wracking because there can be a few things that may be wrong. If you have trouble with your STL structure, I will show you in the DEM part a strategy how you can run some problematic meshes as well. However, the best approach is to use a good mesh. If you have only simple structures, you won't need an expensive CAD system, but you can use Blender. It is very capable in modeling, but with the downside that it works a bit different, and you will not have the possibility to use measurements and parametric modeling like in a real CAD system. I linked my Blender installation so I can call it open with the command Blender in a terminal shell. To do so, I make a new tab with Shift-Alt-T and type in Blender. After Blender is loaded, I select every object by pressing A on the keyboard and then delete. With Shift-A, I add a mesh object in the shape of a cube. The size of the cube can be adjusted to size of the object I want to create. I want it with an edge length of 100 mm. I select 50 mm here, for example, to demonstrate how you can scale up the object using the key S and then type in 2 to scale it by factor 2. To model a shape you want, you have different options. One is to select the face and drag it. This is possible by selecting the object and then clicking Tab to change into edit mode. I dragged the top surface 50 mm in Z direction. Therefore, I changed to face selection by pressing 3 on the keyboard, and then by clicking on the surface, I can move it with the key G. There are a lot of very good tutorials on Blender on YouTube, if you want to get more into this. With the button E, you also can extrude a selection. I will model a chimney above the reaction chamber I created. This is just an example how you can model a STL structure without having access to a commercial CAD program. If you have access to SolidWorks, Autodesk Inventor or similar programs, you can use them as well. However, the meshes created out of them are usually not ideal. How to solve issues with the STL mesh I will discuss later. After the geometry is modeled, I will select the different faces like the reaction chamber, the chimney, the in and outlet of the gas, and divide the structure I created into separate files. Here I'm doing this for the faces of the reaction chamber by selecting all around while holding Shift, and then I separate them by pressing P on the keyboard. You can see it appearing in the top right file browser. Now I repeat the process for the inlet. With the little I button, you can check which part is which. To check the dimensions, Blenders offer nowadays a measuring tool in the edit mode. You can find the tool in the toolbox bar on the left side of the window. I'm just checking if the total dimensions are correct here. The parts are all named cube with a number, because they are all parts of the original cube. To rename the parts, which comes handy during the export, I can click simply on the name of the parts in the browser in the top right corner and rename the individual part. I will call them chimney, react chamber, inlet for the bottom face, outlet for the top face. Now we have all parts that we need for the CFD simulation. The flow enters through the inlet, streams through the reaction chamber and out of the chimney to the outlet. Now I will export the files by File, Export, STL. The files shall be exported to the STL folder in the main directory of our case, because we need them in the DEM and the CFD simulation as well. To select the path, I go into that folder. Since I don't need the original files anymore, I get rid of them. With Ctrl L, I select the path of the folder. I copy the path into the path of the export window of Blender. The name should be ED for Engineerdo with an underline. In the options, I select ASCII, and at batch mode I select object. Now Blender will export the files separated, all named ed_partname.stl. As I said, I have now everything for the CFD simulation. What I actually forgot was the inlet for the particles which I need for the Liggghts DEM simulation. To generate the insert plane, I add a plane with Shift A and then select plane. Now there's a plane which is 1 meter large. To scale it down, I hit S on the keyboard and scale it to a size that barely fits into the reaction chamber. The edges of the plane may have contact with the walls, but they cannot penetrate the chamber walls, otherwise the insertion of particles will lead to problems. The plane is now in the same position as the inlet. For the particle insertion, it would be handy if the insert plane would be somewhere in the top third of the reaction chamber. With the keyboard key G and Z, I can move it along the Z-axis. The plane should be placed not directly on top of the reaction chamber because the particles need some space to be generated without being in contact with the wall. At a third, it should be good here. To export this part, I will follow the same path after renaming the structure, File, Export, STL. But now I use the checkbox Selection Only to not export everything again, but only the insert plane. Therefore, I have to use a reasonable name, of course. I should have unchecked the object mode before. Now I have to correct the doubling names here. In ParaView, it is possible to compare the structures old and new to each other. I deliberately did not change too much, so that the changes are transparent. After opening the main file, you can see that the total dimensions have changed a bit. The new structure is a bit larger in Z direction and probably 2 times as large in X direction. If I make the old cylinder invisible, it's getting clear that the rectangular reaction chamber is in the middle of the old cylinder. The particle insertion plane is roughly at 1/3 of the height of the top of the reaction chamber. It's visible in the side view after I switch from surface to surface and edge view. If you like our content, please give us a thumbs up on the like button. That really helps us to gain more traction on YouTube. I will make a break here and I will get into the DEM modeling in the next video, which will start with a detailed explanation of the script and then bringing in the necessary changes to adapt the new case to the old one. Thanks for watching so far.